Okay, guys, continuing our work here with probability. Some things it's impossible to do the probability of by just doing like a sample. So that's where if we know everything is equally likely, that's where we can do the probability. It says let S be a uniform sample space and let E be any event. So this is where we know we can take the number of outcomes in E divided by the number of outcomes in S. Like how many ways can it happen over how many total ways? And so we can write it like this. We've kind of been doing this, but we've been looking at like tables and stuff with probabilities given to us. Now we're going to look at things that we know the probability of them happening. And so I thought that I would just give you one page for this, and then I went and printed out new notes because this takes a lot of work to do, I think, to work it all out. I also think this is hard. Like I think example 1 I struggled with a little bit, but maybe it was just me. And then example 2, we're going to talk about cards, which I know not everyone plays cards, and again, we'll keep talking about them as well. And then we'll see how long the video is, and I might just stop after these 2 examples. So the first one says, an unbiased coin is tossed 6 times. What is the probability that the coin will land heads? Part A says exactly 3 times. So we want the probability that we get exactly 3 heads, which means that we would get 3 tails as well, right? So the thing is, I don't want to write all these out, right? If we toss a coin 6 times, think about the options. Like you could get heads, 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 heads. You could get heads, tails, heads, tails, heads, tails. Like each coin has so many options. Each coin has 2 options. So think about the bottom number on this. The bottom number is each coin, there's 6 coins, right? Each one has 2 options. So the total number of ways that we could toss a coin 6 times is going to be 2 to the 6th power. Or that means if we wrote out this sample space, there would be 64. This is where it doesn't make sense to write out the entire sample space. So you have to think about it. This is where things get a little bit tougher, in my opinion. Now, what about the top one? How many ways could we get exactly 3 heads? Also a little bit tougher because like the heads could show up like I just wrote, like right there. Or they could be the first 3. Right? Or they could be the last 3. Right? And again, I don't want to write out all 64 options and try to find out those. I don't want to make a tree diagram. So we have to think that from 6 heads, 6 possible times, I want 3 of them to land heads up, and there's only 2 options. So this is where combinations come back to us. Remember we talked about combinations? This is where I'm going to choose from the 6 coins, I want 3 of them to be heads up. And your book says that since there are 6 3 combination ways this can occur, we can figure out that probability. And so, again, if we were just throwing it 3 times, then it would be a little bit easier. But because we're throwing it 6 times, it gets a little bit tougher. This is where I'm okay with you using your calculator on this to get 6 combination 6, choose 3. If you need a reminder of how to do that, let me know. But I believe that we just get 20 on the top. So if we reduce that fraction, we get 5 out of 16. Or that's 0.3125, or 31.25% chance of that happening. Okay? So we know the bottom number is not going to change now, but for each of these other ones, we're going to figure out the other one. So I'm going to do B on this one, and then I put the same problem on the next page. If you're already out of room and you want to use B and C on the next page, that's okay too. But I'm going to do this one. At most 3 heads, right? At most, we get heads 3 times. So again, at most and at least, we have to really think about what that means. So at most 3 times would be 3 or less, right? So that would mean getting 3 heads or less than that. So what if we got 2 heads? That would be 4 tails. Or 1 head. Or None, right? If they could all be tails. So remember when we do or, that means we add these probabilities together. So again, we just did 3 up there. So we know, again, the bottom is 2 to the 6th, or 64. And we're going to say from the 6 we want 3. So for me, A, I had to really think about. But then I knew the other ones were just going to follow this pattern. If I want 2, that's going to be 6 choose 2. Or combination 6, 2. And this, if I only want 1, that would be combination 6, 1. And if I don't want any, there's only one way I could get this, but just to show you, you can do the same process and say 6 choose 0. 6 choose 0 is 1, because that would be all tails. And again, I just use my calculator to get 20 over 64 plus 15 over 64 plus 6 over 64 plus 1 over 64. So that's 42 out of 64. If you want a fraction, reduce it. If you want a decimal, that would be 65.63% chance of that happening, which should make sense that it's going to be a lot higher than exactly 3. So I felt like, okay, I got this pretty good. Now look at part C. And again, next slide here, same question. I just ran out of room. It says, what is the probability that a coin will lead heads on the first and the last toss? So that would be, oh, I put my pin down somewhere and I don't know where. Oh. So again, I'm doing this 6 times. 1, 2, 3, 4, 5, 6. I want heads the first one, and I want heads the last one. And I want, here's the thing. This is where I messed up. I about did it again. I thought it had to be tails in the middle, but it doesn't say on only the first and the last toss, right? So the middle one could be heads or tails. So this one could be heads or tails. This one could be heads or tails. This one could be heads or tails. This one could be heads or tails, which makes it a very different problem. So we got to be really careful that if it said exactly on the first and last toss or only on the first and last toss, then that's a different problem. But this one doesn't say that. So think about how many ways we could get this on the top. So my bottom number is still 2 to the 6, okay? Still 64 on the bottom. That's how many ways it can happen. I want this to happen. How many ways can I get heads on the first toss? Only one way, right? There's just 2 options, and one of them is heads. This is an and, not an or, so this now I'm multiplying. This one, for each of these, it could be heads or tails. So for each of these, there's 2 options because it could be heads or tails, but then the last one has to be heads again. So because we have this specific way to work it out, it's kind of a different setup there. And so that's just 2 to the 4th, right? Which is what, 8/16? Which is 1/4, which is 25% chance of that happening. Okay, we're going to practice some more of these. Maybe I'm making it harder than it needs to be, but I was struggling on that one. I did much better on the playing cards, but that's because I'm really familiar with playing cards. And again, just a reminder about playing cards. Like, I have decks of cards we can look at in class, but 52 cards. This one is all about aces. So there are 4 of each suit in a deck. So there are 4 aces in a deck of cards. That's something to remember. Okay? So also, I want to show you on this one that I think there's 2 ways to do this. I did the probabilities one way, and then the book did them another way. And I just want to show you both and show you that you kind of have options sometimes when you're doing this. So it says, what's the probability that they're both aces if you are selecting 2 cards without replacement? That's really important. So I wrote it like this. I want the probability of an ace, and then I want the probability of another ace. And if I can say the word and, I know I'm multiplying. So I did this. How many aces are in the deck? There are 4 aces out of how many cards in the deck? 52. But I'm not replacing it. So when I don't replace it, there are now only 51 cards in the deck, and there are now only 3 of them that can be an ace. And if I did that, I just did it on my calculator and got out a decimal, which would be like a 0.45% chance that I'm going to be able to do that. It's actually going to be the probability of choosing any 2 of the same card in a row. Or here's how your book did this. Thinking about what we did with the combinations with the coins. If we wanted to do a combination of how many ways could I choose 2 cards out of a deck of 52 cards, I could say the number of ways that I could do this would be 52, choose 2. That's the total number of ways it can happen. But the top number is how many ways can I draw aces, 2 aces from how many aces? 4 aces. So if there's 4 total aces, I want 2. And guess what? You get the exact same answer, which is 1 over 221, which is the same answer if you take 4 over 52 times 3 over 51, you get 1 over 221. So I don't know what way you think is what you think is better. I think for me it depends on the problem of how I set it up, but I just want to show you that that gives you the same answer. So think about that for part B. If I wanted the chance of neither of them being an ace, so I want the probability of not an ace and the probability of not an ace. So doing it as fractions like this is how I thought of it, but as soon as I saw the answer for part A, I realized I could set up a combination as well. So I'm going to do this one both ways as well. So see if you can do it and see which way you would set it up. If you don't have a calculator, tell me what you would multiply together or what combination you would do for this. So again, my bottom number is going to be 52 cards if I set it up as a fraction. And then when I don't replace it, my next one's going to be 51. But now my top number is going to change, right? It's going to be a lot better probability that there are 48 cards that are not aces. And then one less than that would be 47. And when I multiplied that together, I got 0.851. And again, I rounded because it kind of went on forever. But think about, yeah, do you agree with that? What if we did it as combinations? The combination here would still be 52, choose 2. But now, how many cards am I choosing from? To not choose an ace would be 48, choose 2. And again, you get the same answer. Okay? Okay. So, yeah, we're